Okay, maybe you can start, but maybe.
Okay.
But only 10 persons.
Should we start?
Okay. You start the recording. Okay.
All right. So welcome everybody to this first session of this today. I'm Yuji. I'm chairing this session. So without further ado, let me introduce the first speaker here, who is Roberto Ruboli, who is going to talk about the additivity of the relative entropy of entanglement generalization. So Roberto, please.
Okay, thank you very much. So this is a joint work with Marco Tomamichel at CQT in Singapore. And yes, exactly, I will talk about additivity properties of relative entropy of entanglement and some generalizations. So first I will introduce what are entanglement monotones and the additivity question. Then I will state some additivity properties of the relative entropy of entanglement, and I will identify two classes. And I will generalize it to some more general quantities, and these are called alpha Z Renyi relative entropy of entanglement, and I will still state some additivity properties of them. And I will mention some application of the results to catalytic transformation. And in the end, I will talk about the non-additivity. In this case, a more general setting, so entanglement monotones based on any quantum relative entropy. Anyway, so what are entanglement monotones? First, I define separable states. So we assume n parties, and a separable state is a convex mixture with probability distribution, I call it PI, of tensor products of local states. So we have n tensor product of local states, and otherwise, if the state is not separable, I will call it entangler. So what is an entanglement monotone? An entanglement monotone is something that somehow quantifies the entanglement content of a state. So it's a function, I call it R, from the set of states to positive values. And the higher is the value, basically, the higher is the entanglement. And one property that basic properties that is required is that it doesn't increase under any local operation and classical communication, which we call LOCC and standard way. And yeah, under this LOCC, you cannot create entanglement. So the value of the monotones must decrease. And some examples are relative entropy of entanglement, generalized robustness, but of entanglement. But there are many out of there, and many have been studying. And as you understand, I will mainly focus on relative entropy of entanglement. And so let's start with the additivity question. So I have my monotone R and two states, ρ1 and ρ2. Both of them are entangled, but they are in tensor product, so there are no correlations between them. And I'm asking, is the monotone evaluated on the tensor product of the states equal to the monotone evaluated on the first state plus the monotone evaluated on the second state? And this would mean basically, is the entanglement motivated, the entanglement defined by this resource monotone, so motivated by this resource monotone of the whole system, ρ1 and ρ2, just the sum of the entanglement of the two systems is, or there's something else. And so one question is R additive for any states ρ1 and ρ2? And I mentioned that this is not true for many monotones, and these are some old, these were already known for the relative entropy of entanglement, for example, for 20 years ago, and for other monotones like the generalized robustness. And maybe this is not the most interesting question. Anyway, I will address it later. But what I'm only interested about is what are the minimum requirements on the states ρ1 and ρ2 to ensure additivity. And also in this way, there are some results, but I will be interested in the results that are out of there are partial, or they require both constraints on ρ1 and ρ2. And what I will look for is can we just constrain the first state, and can we still have additivity? So like the theoretical question, which are the minimum requirement for additivity? And actually, we find that I just need to impose some constraints on the state, on the first state, actually. So, okay, let's go through the results. So first, the additive, the relative entropy of entanglement. So I just, I guess now any of you is familiar, I just define the relative entropy with trace rho log rho minus log sigma when the support of rho is smaller than the support of sigma, otherwise it's infinite or basically not defined. And the relative entropy of entanglement is just, you just minimize over the set of separable states the relative entropy. And so the first result, so we introduced what are maximally correlated states. So maximally correlated states are bipartite states of this form, sum of jk, rho jk, jj, kk. And so you can think of them as a generalization of bipartite pure states. You just write your state in the Smith decomposition, you build a density matrix, and a bipartite pure state, you can see that is just a generalization of maximally correlated states. And the first result we have is that only when the first state is maximally correlated, then for any state ρ2, whatever its nature is, the relative entropy of entanglement is going to be additive. So the relative entropy of entanglement for one test ρ2 is equal to d ρ1 plus d ρ2. The second result we have is a bit more complicated. So here we have n-partite states. And so we have some condition on the optimizer of the relative entropy of entanglement. So if tau1 is an optimizer that, in particular, if commutes with the input state and the product with the inverse of the optimizer multiplied by in the density matrix sense with the input state is non-negative. So non-negative, I mean, it has positive entries. So in a product basis. So you look at your matrix in a product basis, and then you can find a basis such that it has positive entries. Then for any n-partite state ρ2, we have that the relative entropy of entanglement is additive. And this class includes separable states. So basically tensoring any state with any separable state, it doesn't increase the relative entropy of entanglement. Bell diagonal states, generalized decade states and isotropic states, and probably many other, but this one were kind of some states were considered in the literature. So I just mentioned them. So actually I wasn't, our research was motivated by not really the relative entropy of entanglement, but to look at some other monotons. And so I'm asking what are the additivity properties of the other monotons? But before doing that, I will explain the main idea. So the main idea is to use the condition of local minimum. So I call it tau, the optimizer in the minimum, and I take the derivative sigma. In this case would be a Frechet derivative. So in the derivative along the direction sigma in a density matrix sense. And here we have an expression for the condition of the minimum. So since the relative entropy is convex in the second argument, we have a condition, an if and only if condition for an optimizer. So if the condition would be if this trace function of sigma, where sigma is any separable state with a positive operator that I call chi of rho tau, in tau is smaller than 1 for any separable states, then we know that tau is an optimizer. And the idea is to show this, is to show that for the tensor product ρ1 and ρ2, the optimizer is the tensor product of the optimizer of the marginal problems. So we have the constraints by assumption on both ρ1 and ρ2 and their optimizer. And then we add further constraints on ρ1 and tau1, for example, for maximally correlated states, or for the other class, I added other constraints because otherwise it wouldn't be actually additive. So you need other constraints. And in this way, I'm not going into the details, but you can show that it is additive for the classes I mentioned above. So now generalizations. First I introduced the alpha Z Renyi relative entropy. And this one provides a framework to address different families of Renyi divergences. So the definition is let alpha between 0 and infinity, 1 we just define it in 1 with the limit, and Z is strictly positive. Then we define it in the way you see it in Formula 11. It's just you can think of it as generalization of the relative entropy, but includes more families. I will talk about it later. And we also introduced the related monotone just with the same idea, so minimizing over the set of separable states. This basically ensures that whenever the underlying divergence satisfies the data processing inequality, then the minimized quantity is going to be a monotone. This is just a straightforward idea. And so here is a picture. Is the alpha Z plane to show a bit which quantities I can get with the alpha Z relative entropy. So the line alpha equal to Z, we get the sandwich relative entropy. If I guess many of you are familiar, for Z equal to 1, you will get the PETS one. And then you have some points. So the infinity point would be the Dmax. The 1/2 point would be minus log fidelity. The alpha equal to 1 point excluded Z equal to 0 is going to be the omega relative entropy, and the mean entropy would be alpha equal to 0 and Z equal to 1. Now I will discuss some well-known points. So as you can get whenever we have the omega relative entropy, then the minimized quantity is going to be the relative entropy of entanglement. So alpha equal to 1, Z excluded, Z equal to 0 excluded. We have the relative entropy of entanglement. In the point at infinity, we have the generalized robustness, which is also just a quite well-known quantity, and this one quantifies how much mixing can take place before you get your state. Like if you have an entangled state, how much mixing can take place before you get separable, basically. And then alpha equal to Z equal to 1/2, we have the geometric measure of entanglement. And this one for pure states is just defined as the fidelity, maximum fidelity, so the maximum superposition with pure product states in this case, because the state is pure. Pure product states are, the extreme points of the set of separable states. And for mixed states, we have the convex roof construction. But actually, with some further work, you can show that the 1/2 point is going to be minus log 1 minus the geometric measure of entanglement, which is minus log fidelity fs of rho, which is the fidelity of separability. So in terms of fidelity, is the maximum distance between your state and the set of separable states. Okay. So also here we can show in the same way that for maximally correlated states, regardless the nature of the state ρ2, this is going to be additive. And the same is happening with the same constraints on the first state. So also the second results we had for the relative entropy of entanglement generalizes for this alpha Z. And what I can say is that our approach was quite general. Okay, so I will go through it now. But okay, for the alpha Z relative entropy, we can still get some condition of minimum. These were not known. The relative entropy was known before, but it was not used to study additivity problems. But these ones, it's a bit more general, and this condition were not known. They are a bit complicated, but you can still manage to get through them and show that the optimizer of ρ1 tensor to ρ2 still factorizes as the tensor product of the optimizer of the marginal problems. And you can see how where this is going through is we can actually see that we can replace the set of separable states with the set of free states, and we can actually study additivity problems in n-resource theories, and this is what we are starting to do. And we also have we can prove that also, for example, in resource theory of coherence, for the one that you are more familiar, these quantities are going to be additive for any states. But this resource for coherence was kind of already known, but yeah, we can still recover it. So one thing that maybe I want to mention is that this approach is quite general, and we could do it also for the monotone based on the geometric Renyi divergence, but we couldn't have a strategy that could find these results for any quantum relative entropy. Yeah, and this is something that we are still thinking on. Okay, so okay, why am I interested in this result? One motivation might be, okay, what are the fundamental limits? So in catalytic transformations. So this is an application, and yeah, okay. So here an example. So whenever we have two states, psi and psi prime, both of them pure, bipartite pure, and we want to transform them, maybe it's not possible to transform them with LOCC just in the one-shot setting, but adding a catalyst with a colleague nu and acting on the whole system plus catalyst with a map and asking for the catalyst to be unchanged at the end of the transformation could allow actually the transformation from psi to psi prime. This phenomenon is called catalysis. And here, there is some interest in understanding the power of mixed catalysis. And this additivity question can provide some set of necessary conditions. So in the first line, I have my monotone evaluated on psi plus the monotone evaluated on the catalyst nu. And here I have additivity, so I can just is equal to the monotone evaluated on tensor product, and then I can use just data processing inequality. So basically monotonicity under LOCC, which is why it is a monotone. And then I use additivity again. And in this way, I can simplify the catalysts, and then I can get this all constraints on the set. I call it D is the set. If you remember the picture before of the alpha Z Renyi relative entropy, is the set where it satisfied where it was blue, right? So it's the set where it satisfies the data processing inequality. So the monotone related is going to be actually a monotone. So it's not increasing under LOCC. Yes, so here you have a whole set of constraints, and actually for bipartite pure states, we also have a nice expression of the alpha Z evaluated on pure states, and you have this, and it is equal aqua to h bit of p. H bit of p is the Renyi, yeah, the Renyi quantity. So you know, yes, and we have this natural. The classical Renyi entropy of some classical coefficients, and we have this nice duality relationship 1 minus alpha over z plus 1 over beta equal to 1, and yeah, it's quite nice. And another point is that we were studying the catalytic setting, and in this case, not really the relative entropy of entanglement was crucial, but the alpha equal to z between 1 alpha and 1, what is called the sandwich Renyi relative entropy, 1 excluded, and 1 was excluded because somehow for pure states the relative entropy of entanglement and the squash entanglement coincide, and the squash entanglement is super additive. So there, okay, I'm not going into the detail, but there I'm not interested actually in the point 1, even though it's a more popular. So in some setting, you might be more interested in actually in other ranges other than just 1, so the relative entropy of entanglement. And here we use these additivity results to actually find out that in correlated catalytic transformation for a small error, you need a divergent catalyst with the amount of correlation. So it's logarithmic 1 over epsilon. Yes. So last questions. Non-additivity of entanglement monotone based on a quantum relative entropy. Okay, I mentioned some results were already around. So it was already known that relative entropy of entanglement is not additive. The generalized robustness of entanglement is not additive, and many other results. But we kind of wanted to unify this under the same under a more general framework. So here we can do it. So we have a quantum relative entropy, and we define the monotone, related monotone just minimized over the set of separable states. And actually we find that any monotone defined in this way with any quantum relative entropy, then it's not going to be additive. So here by quantum relative entropy, I mean something that satisfies data processing inequality. I guess any of you is well familiar with all these quantities, so it is not increasing with any quantum channel epsilon, E, or additivity under tensor product, or normalization condition. You can read them through. And so, for example, the relative entropy is satisfying these conditions. All the alpha Z Renyi relative entropies too, the geometric Renyi divergence, but actually this is more general. And so we can find that for antisymmetric states, actually it is not additive. So the monotone evaluated on the tensor product of two states is going to be for dimension big enough equal to the monotone evaluated on a single state. And this is different from 2 times the value of the monotone evaluated on a single state. So it means that it's not additive. And so, yeah, maybe some words, the way we do it is we can calculate with our expression for all the alpha Z range for whenever this D is an alpha Z Renyi relative entropy. And when we have the points at 0, so alpha equal to 0 and Z equal to 1, so the mean divergence and the D max, so alpha equal to Z equal to infinity, we can calculate the quantity on these 2 points for both the single state and the tensor product of 2 states. And what you can find is that it gives the same value. So basically we can sandwich all the quantities inside there. And so any divergence is going to give the same value for rho minus tensor rho minus and rho minus. And you can actually compare that these 2 values are not one the double of the other, so it's not going to be additive. And yeah, another remark is that the same holds for the when the minimization is replaced over the set of PPT states. So also in this case, these monotones wouldn't be additive. And so this is quite general. Yeah, maybe I remark again that for the additivity results we needed a structure, even though it was quite a general structure. So for the alpha Z, or for I didn't mention it, but also for the geometric divergences, we could do it for both of them, but we couldn't identify like some general properties. But this actually holds for any the non-additivity results also holds for any quantum relative entropy. Okay, I'm done. Thanks.
Yeah, thanks a lot, Roberto, for a nice talk. So is there any question? Okay, so Mark has a question. You can unmute yourself and ask.
Okay.
Thanks for your talk.
Thanks.
Can you go to the slide with the relation between the maximum separable fidelity and the geometric measure?
Yes.
That one. Yeah.
Hmm.
The equality on the last line. Can you give a hint as to how that is shown?
So this is not my result. So this is a paper where it's like linking a distance measure with its convex roof. So I think it's shown through Ullmann's theorem, but I'm not proof. I didn't really go through much the proof, but there you can show a correspondence between the convex roof construction and just the maximization of over the set of separable states. Yeah, I think
for that?
I think it's from Alexander Streltsov and some other authors. It's a quite famous result.
Okay.
Yeah.
If you have the reference,
Yeah.
it'd be
Okay.
helpful to put it in the Zoom chat or Slack or whatever.
Okay. Okay. I will send it to you.
Thank you.
You're welcome.
I have a question. Hello.
Yes.
So could you back to the theorem 1 and theorem 3, both?
Yes.
I think this time is already shown in my book. At least many reference already noticed. I think with this one.
So I think what you are talking about is these two references I have here.
Not only this one, also my old book also discussed that in the case of maximally correlated states, so many things become additive.
So for what I could find,
And
only when both states are maximally correlated states, not just when one state is maximally correlated.
maybe I need to check, but at least in the case of formation also satisfy additivity, and in that case, only one state should be maximally correlated.
Okay, you can send me the reference.
Okay,
and
okay,
I will
also theorem 3.
Yes.
Theorem 3 is in the case of you consider in the case of yes.
This one?
Yes. So of course, my paper with Honjuan, that journal physics A, we only consider sandwich Rennie and test version, but I think we already discussed that equality.
Yes.
In the case of test divergence and sandwich divergence, but
yes.
generally G is not discussed, I think.
Okay. So I'm quite familiar with the paper I cited, but if you have other references, so in that paper you ask for maximally correlated for both row 1 and row 2, and the way you can do it is quite different because there
yes, at that time, okay, both maximally correlated, yes.
Yeah,
Okay.
and there you can use the results for resource theory of coherence, which you can get from the conditional entropies. But in this case, without any constraints on row 2,
row 2 is general. Okay, I see.
row 2 is general. Is gonna be a completely different proof, and actually we were motivated. We didn't want to add any constraints on row 2 because we want to find in some protocols, like in the catalytic setting, some assumption without some condition without requiring any assumption on the state row 2. So that was mainly our motivation.
Okay, I
understand.
understand.
Okay, no worries. I see a message. Okay, if you have time for another question, Mark, you can.
Sure, go ahead.
Yes.
Thanks. Can you go to the slide with the integral representation function? That's one, but I think the other one was a bit simpler.
Yes, for the relative entropy. Yes, this one.
This one. So it's very interesting, this finding. Can you give a sense of how it's useful? Because there's the computational problem of the relative entropy of entanglement, finding the tau. And then you've shown, in some sense, there's this equivalence to equation 10. The condition before equation 9. It seems like it's just as hard to check. And so
no, it's gonna be
what's that?
It's gonna be much easier because we have a maximization. It's a linear functional, so it's 3 sigma.
Okay, good.
So just maximization of pure product states. So actually, you can. It's gonna be much easier. You don't have the convex combination.
So if you're trying to find the tau,
so okay,
make some guess for it, like an ansatz, and then check this condition.
So it depends what you want to do. So also we have we can find the tau. So we have an ansatz, yes, But in the case of additivity, we don't actually need an answers. We just need the two condition of the marginal problems without knowing tau. We just know that tau satisfies some conditions, and then we can prove the additivity. But if you want to integrate the measure, the quantity for a specific state, and we also did it, for example, for pure states, I showed the expression, this one here. What you can do, you can guess the optimizer tau, and then you can check this minimization problem. But now it's going to be easier because it's going to be just on few product states. And then if it actually, you can show it analytically that it holds, then you know that your optimizer is the true optimizer. And this is also quite a strong method as I can, but as I think of it. But yeah, for additivity, actually, you don't need to just answer the explicit form of tau. Actually, for maximally correlated states, we don't know the optimizer, for example. We know some structure of it, but yeah, you don't really need for additivity to know the optimizer.
Okay, thank you.
You're welcome.
All right, so let's take other questions to the Slack channel discussion. So let's thank Roberto again. Thanks for a nice talk.
Okay, thank you very much.
All right, so is Hayato there? Can you? Right. So can you share the screen?
Can you hear me?
Yes.
Okay, and can you see the slide?
Yes, I can see the slides.
Okay.
All right, so let's go to the second talk in the session. The second speaker is Hayato Arai, who is going to talk about the pseudo-standard entanglement structure cannot be distinguished from a standard entanglement structure. So Hayato, floor is yours.
Thank you for the introduction. I'm Hayato Arai from Nagoya University. This is a joint work with Masashi Hayashi, and the archive number is this. If you want to know about details of this talk, please check it. Okay, first of all, we give the brief story of our study. We explain definitions and details later. This talk is addressed on general probability theories. General probability theories, here after GPTs, is a generalization of the model of quantum theory with state space and measurement space. Then, our interest is characterization of entanglement structure. Entanglement structure is a possible structure of quantum computer system in GPTs. In standard quantum theory, the structure of computer system is uniquely determined by the tensor product. However, in GPTs, the structure is not uniquely determined, even if the local systems are completely equivalent to the standard quantum theory, and even if we impose natural postulate about local structures. In other words, the standard entanglement structure is not trivially determined by natural setting about the probability and natural assumption of local structures. Then, many other models are theoretically consistent with natural postulate. Therefore, it is important problem for foundation quantum theory to derive the standard entanglement structure from possible entanglement structures by additional reasonable postulates. This study clarifies the difficulty of this problem. In our study, we introduce a kind of structure so similar to the standard entanglement structure that it cannot be theoretically denied by verification of maximally entangled states with small error. When such similar entanglement structure satisfies self-duality, we call it shared standard entanglement structure here after PSES. Self-duality is important property of standard quantum theory, and it is related to projectivity of measurement. Then we consider the problem that, is there any example of PSES except for the standard entanglement structure? Our result possibly answer this problem. That is, we show that there are infinite examples of PSES. In contrast to the similarity of PSES, we show the difference between shared standard entanglement structure and the standard entanglement structure in terms of performance of state discrimination. So we showed that some of example of shell standard entangled structure can discriminate non-orthogonal states perfectly by one-shot measurement. And besides, we investigate a diversity of entangled structure with group symmetry. And we showed that a kind of global unitary symmetry determines entangled structure as a standard one uniquely. Roughly speaking, a kind of group symmetric condition denies possibility of such shared structure. Okay, let's start to talk about details. We talk on these outlines. First, as a preliminary, we simply introduce GPTs and entangled structures. Second, we explain our setting and results. Finally, we summarize this talk and give some problems. Okay, first we give a simple and brief introduction to GPTs. GPT is a framework that contains states and measurements. The framework is a generalization of quantum theory. Because of the simplicity and easy understanding for beginners about GPTs, we only explain a restricted class of GPTs. And in order to introduce the restricted class, we start the definition of the model of quantum theory, standard quantum theory. In this talk, we consider finite dimensional Hilbert spaces, and we denote the set of Hermitian matrices and the set of positive symmetric matrices as Th and T plus H respectively. In standard quantum theory, a state is defined as a density matrix, and the measurement is defined as a positive delta value measure. When a state law is measured by a P of MI, then the probability to get an outcome I is obtained by the trace. In this way, the model of quantum theory is defined by set T plus H. Here we remark that the condition that effects of the P of M are positive semi-definite can be translated to this condition. The trace is positive for any state law. And in terms of probabilistic structure, the important thing of this setting is these two conditions. These two conditions are derived from the definitions of states and measurements, and these two conditions imply that the trace consists of probability distributions. And the essential conditions also hold when we replace the set T plus H with more general set K. This is a definition of a model of GPTs. In contrast to the set T plus H, a model of GPT is defined by a set K called a positive cone. Here we omit the definition of a positive cone. If you do not know the definition of positive cone, please consider a subset of Hermitian matrices consistent with certain probabilistic postulates. And K means K means the set of unnormalized states in the model. But the important thing is these two conditions also hold in this setting. Here, the set corresponds to the effect is changed to the dual of K, but the dual of K is defined by this condition, and this condition is the same as that of quantum theory. Okay, this is a definition of the model of GPTs. The GPT is a generalization of the theory defined by a positive cone K. Okay, next we explain entangled structures. Here we denote entangled structures ES. ES is a possible structure of the model of the bipartite composite system of quantum subsystems in GPTs. In physical system, we only know the model corresponding to the set of positive semi-definite matrices on the tensor product of sub-Hilbert spaces. Here we call this model the standard entangled structure, here after the CES. However, in GPTs, entangled structure is not uniquely determined as the CES, even if we assume local system is completely equal to the model of quantum theory. some tuples of such fundamental operational postulates derive that entanglement structure K satisfies this inclusion relation. Here, the tensor product is defined as the set of unnormalized separable states, and the dual of the separable states corresponds to the set of entangled witnesses in quantum information theory. In this talk, entangled structure is defined as a model defined by K with this inclusion relation. There is no known reasonable operational property to characterize a set from such a range of entangled structures. Then it is important problem to derive the set from entangled structures by reasonable postulates. In this talk, we show the difficulty of this problem. That is, we show the existence of shared structure of the set. Okay, next we explain our setting and result. We consider entangled structure with the following two conditions as shared standard entangled structures here after PSES. Strict mathematical definition is given later. Anyway, the first condition is called undistinguishability. This means availability of verification of any maximally entangled state with small errors. Verification of maximally entangled state is important task in quantum physics to guarantee that the system fully contains quantum object. However, an experimental verification with some errors does not guarantee that the prepared state is exactly the same as the target maximally entangled state because of the error. Therefore, this condition holds not only in the set but also in another entangled structure. And the second condition is self-duality. Self-duality means the state space and the effect space is essentially equivalent. Mathematically, this equality is a positive and its dual. Self-duality can be regarded as the saturated situation of pre-duality. Pre-duality means pre-duality means this inclusion relation, and pre-duality corresponds to availability of projective measurements. Hereafter, we discuss the existence of such structure, and we assume the dimension of subsystems are equal because we need to consider maximal entangled states. Okay, we explain the details about the definition of PSES. First, we introduce undistinguishability. Let us consider whether the following task is possible or not. In order to prepare a maximally entangled state, sigma, we prepare a state rho in our model and verify that rho is almost equivalent to sigma with error probability epsilon. In order to success such a task for any maximally entangled state sigma, our model includes near state rho for any given maximally entangled state sigma. This task is successful if there exists such a state rho in the model. In other words, if entangled structure has a state sufficiently near any maximally entangled state, then K success is this task. So there are possibility that another entangled structure satisfies this task. For example, entangled structure with this inclusion relation successes this task because the structure has all standard quantum states. Then we consider this concept mathematically. Such a verification is implemented as hypothesis testing. Because the error probability of hypothesis testing is given by the trace norm, then we define the value d of k, defined as this. Simply speaking, the d of k is such a largest distance between k and the maximal entangled states, like this figure. This value means how small error we can verify to exist maximally entangled state in the structure K. For example, if d of k equal to 0, K contains all maximally entangled states. That means we can verify to verify to prepare all maximally integral state theoretically without errors. Then we consider the condition d of k less than epsilon. And we call this condition epsilon undistinguishability condition, because this condition implies that we cannot deny the possibility of structure K by preparing maximally integral state with epsilon error verification. Next, we introduce the importance of self-duality. Here we simply point out the relation between projectivity and pre-duality. In foundation of quantum theory, projectivity is well considered as the postulate of quantum theory. And there are many versions of projectivity in foundation of quantum theory. In this talk, projectivity is the following property. For any pure effect E, there exists a projective measurement EI, such that an element EI is equal to E. And here, projective measurement means that the post-measurement state of this is given as the normalization of the effect. Projectivity derives pre-duality as follows, where pre-duality means, pre-duality means this generation. So the dual cone is generated by pure effects, and there exists a projective measurement that is a correspondence of effect and the normal state. Therefore, any element in the dual is included in the original cone K, because K is the set of a normalized state. Actually, the present version of the archive paper is not based on this discussion about the relation between projectivity and pre-duality. We will revise this. Anyway, in this way, pre-duality is introduced by projectivity, and self-duality is regarded as saturated situation. That state space is restricted and effect space is expanded with preserving projectivity. This is non-trivial statement that pre-dual cone can be modified self-dual cone always. This is shown as a statement later. Now we define epsilon PSES as an entangled structure with epsilon undistinguishability and self-duality. The standard entangled structure is an example of epsilon PSES for any epsilon larger than 0, but no other simple example is not found. Our question is that, is there any example of epsilon PSES for small epsilon, but for the CES? This is the main question in this study, and the answer is yes. We show that this theorem that is for any positive epsilon, there exists an infinite number of exactly different epsilon PSES. This is the main result. In this way, the possibility of such shared structure cannot be theoretically denied by experimental verification of maximally integral state with tiny errors. Because for any tiny epsilon, there exists integral structure satisfying the epsilon undistinguishability. So in order to show this theorem, we give a general theory of self-dual cones. First, we obtain the following theorem. For any given pre-dual cone K, there exists a self-dual cone tilde K satisfying this inclusion relation. Simply speaking, a pre-dual cone can be modified as a self-dual cone, this theorem stated. So in this way, repeatability and self-duality is connected by our theorem. Someone might consider this theorem is trivial, but this theorem is not trivial mathematically. Actually, for the proof, we need to apply Solon's lemma, and therefore, this self-dual modification is not given constructive form. Due to this weakness, it is difficult to show that two self-dual modifications are strictly different, even if pre-dual cones are strictly different. For example, when we obtain two different pre-dual cones, but both of their self-dual modification might be equal to the CES. In such a case, we cannot show the existence of self-dual cone, but for the CES. This problem is resolved by the following theorem. Simply speaking, when we obtain the exact hierarchy of radial cone, exact hierarchy means such a strict inclusion relation. And then there exist exactly different self-radial cones satisfying this inclusion relation. So if we want to show the exactly different existence of infinite many self-radial cones, we have to take an exact hierarchy, infinite depth of radial cones. So due to time constraint, we skip about the idea of the proof, these theorems for a moment. If we want to know this, please ask in question time later. Sorry. Anyway, so then we show the existence of epsilon PSES by main theorem 2. In order to apply main theorem 2, we need to construct an exact hierarchy of radial cones. In our paper, we construct radial cone KR with a parameter R. And we can construct KR with satisfying this inclusion relation. So KR is an exact hierarchy of radial cone. Then, therefore, main theorem 2 implies that the self-radial modification tilde KR is exactly different. Also, we need to estimate D of tilde KR. Self-radial modification is not given as a constructive form, but the value D of dual KR is larger than any other self-radial modification of KR. And the way of construction of KR enables us to estimate the value of T of dual of KR less than epsilon for sufficiently smaller. Therefore, the self-radial modification satisfies epsilon distinguishability. So, and because epsilon is arbitrary parameter larger than 0, we obtain the following theorem. That is, for any possible epsilon, there exists exactly different infinite epsilon PSES. Here, infiniteness is shown by the arbitrarity of epsilon. Now we give other results. We also show that some example of epsilon PSES has extraordinary performance of perfect state discrimination. Perfect state discrimination is a fundamental task in quantum information theory. In the standard entangled structure, perfect distinguishability of states is equivalent to orthogonality of states. However, we showed that for some epsilon PSES, there exists a measurement and perfectly distinguishable non-orthogonal states by the measurement. In this way, there exists such shared structure that cannot be denied by verification of maximally entangled state, even if the structure has extraordinary performance for discrimination tasks. On the other hand, we also show that a kind of group symmetry condition this characterizes the sets uniquely. In this paper, we consider such symmetry about a subgroup of general linear group on Hermitian matrices, and consider global unitary group defined as this. And as a result, we show that global unitary symmetric entangled structure is uniquely determined as a set. Finally, we simply summarize this talk and give some open problems. In GPTs, there are many possibilities of entangled structures. Especially, we introduce epsilon PSES as an entangled structure with epsilon distinguishability and self-duality. Then we showed that there exists infinite example of epsilon PSES for possible epsilon. This result implies that self-duality is not sufficient for the determination of the sets. Also, we show that some epsilon PSES can discriminate non-orthogonal states perfectly. And this result clarifies that verification of maximally integral state with errors cannot deny the possibility such a shared structure, even when such shared structure has extraordinary performance for state discrimination, which implies the conjecture that the equivalence of orthogonality and state distinguishability can characterize a space. This is also an important problem. This is an important problem. I'm sorry, we explain. So our proof is just showing the existence of such shared structure. Of course, it is there is a possibility that such a shared structure can be given as a concrete constructive form, but such a construction of epsilon PSES is of a problem. So moreover, we show that global unitary symmetry characterizes the sets from integral structures. However, the condition about global unitary symmetry is quite strong because the aim of GPT is to derive such symmetric structure from operation postulates. Our contribution is to point out that group symmetric condition is essential for the sets. So the reasonable symmetric condition is at most local unitary symmetry, LU. And then it is also an open problem whether LU symmetric PSES exists, but for the sets or not. This is an open problem. That is all. Thank you for your attention.
Thank you, Hayato, for a nice talk. So is there any question?
I would like to have one. Thank you for the talk.
Yes.
My question is, one of these GPTs that are well known is the so-called box world. I'd like to make sure, is it true that there is no entanglement structure there? Or, I mean, in that case, for that GPT?
Yeah. Or, in our setting, so instance setting, entanglement structure is a model by defined a positive con K satisfying this inclusion relation. But standard definition of a box world is not satisfy this inclusion relation. So
sorry, so it is your theory is based on this Hilbert space behind, right? Construction and the usual tensor product. Okay. I see.
But we remark that we emphasize that we define, of course, Hermitian matrices on Hilbert spaces, but we do not assume the structure of positive semi-definite matrices. So this means that we don't assume that vector space as bracket state.
Okay, thank you. I see. Yeah, thank you very much.
Thank you.
Is there any other question? So I think you focused on the verification of a maximally entangled state. So
yes,
given some theory like epsilon pseudo entanglement structure, is it possible to differentiate that with a standard entanglement structure used in a different state, possibly, rather than a maximally entangled state?
Sorry, do you? So you mean that can we relax the maximally entangled state other than other entangled states? Sorry. What do you mean?
If you consider a different, like different entangled state.
Maybe the assumption of maximal we restrict maximally entangled state is technical reason, but maybe I think I believe that such a realization is possible. So we can consider more general condition the verification of not maximally entangled states. But this
Okay.
is also open.
Okay, right, thanks. So let's take other questions offline. So let's thank Hayato again for a nice talk.
Thank you very much.
All right, so let's move on to the next talk. Is Satvik here?
Yes, I'm here. Can you hear me?
Great. Can you share the screen?
Yes, just a second.
Awesome. Great. So let's move on to the next talk. The next speaker is Satvik Singh, who is going to tell us about the disability of entanglement. So please.
All right. Thank you for the introduction. I'm going to talk about some good old entanglement theory today. This is joint work with my PhD supervisor, Nilanjana, at Cambridge. All right, so this is the archive identifier for those of you who are interested in more details. All right, so let me jump right into it. So usually entanglement distillation is studied in a bipartite setting. And the basic task in this distillation procedure is that there are two parties, Alice and Bob, and they initially share, let's say, n copies of some mixed bipartite state, let's say rho AB. And their aim is to obtain some mn copies of the Bell state, of the 2-qubit maximally entangled state, by using only local operations and maybe some classical communication. Now, the one thing to note here is that the classical communication configuration between the two parties matters in this procedure. So if we allow communication only in one direction from Alice to Bob, then this is a different task. And then maybe if you allow backward communication from Bob to Alice as well, then maybe you might be able to do better because you're adding another resource. So if you just have one-way communication, then we say that the procedure is one-way LOCC, or if we have back and forth communication between the two parties, then we call the procedure two-way LOCC, or two-way local operations assisted with classical communication. Now, if in the asymptotic limit of the initial number of copies of the state going to infinity, if the distance between the extracted mn copies of the Bell state goes to 0, then the rate at which these Bell pairs are being generated in the asymptotic limit is called an achievable rate for distilling entanglement from your original state. And it would be either called one-way achievable rate or two-way achievable rate, depending on what kind of classical communication configuration you allow between the parties. And then finally, what you just optimize over all possible one-way LOCC or two-way LOCC operations to arrive at the quantity of interest, which is the one-way or two-way distillable entanglement of the state. Now, clearly, two-way distillable entanglement is going to be at least as large as one-way distillable entanglement, because as I said, if you're allowing backward communication as well, then you're allowing the parties to more resources essentially. And so this just essentially follows by definition. All right, let us also recall that a bipartite state is called separable if it lies in the convex hull of product states. So basically you can write it as a convex mixture of product states. It is called PPT if it remains positive under the operation of partial transposition. So you just apply transpose on one part and your state stays positive under that. If it stays positive under this operation, then it's called PPT. We call the state two-way undistillable if the two-way distillable entanglement of the state is 0. And similarly, we can define one-way undistillability. Now, clearly, I mean, all these forward implications from 1 to 2 to 3 to 4 are well known. In particular, it is also known that this 1 to 2 implication is strict, or in other words, there are PPT states which are not separable. And the implication from 3 to 4 is also known to be strict. meaning that there are states which are one-way distillable, but they may not be two-way undistillable. However, we do not know if the 2 to 3 implication is strict or not, and this constitutes the famous NPT-bound entanglement problem. So we do not know if the PPT property of a state is equivalent to its two-way undistillability. In other words, we do not know whether every NPT state or every non-PPT state is distillable or not. And this relates to the problem that we're going to see next. All right, so now what we're going to do is we're going to bring in a third party, let's say Eve, so that the three parties, Alice, Bob, and Eve together share a purification of the original bipartite state rho AB. And then in this setting, Alice will then share the complementary state, which is just defined as, instead of tracing over the environment or Eve, you now just trace over Bob, and then you get a separate, a different reduction, rho AE, which is called the complementary state of the original state AB now. And in the usual distillation setting, if Alice and Bob are performing the distillation procedure, then as maximal entanglement is established between Alice and Bob, Eve gets more and more uncorrelated from both the parties, right? This follows just from the monogamy of pure maximal entanglement. But now imagine that Eve is not really our adversary, but is actually our friend. Eve is now our friend, so that Alice can also classically communicate with Eve, so that Alice can either choose the reduction with Bob, that is rho AB, or the reduction with Eve, that is rho AE, in the distillation scheme. And depending on which of these two states gives her the best rate of distilling entanglement, she can choose either one of these. And so we obtain these 4 max distillation quantities, depending on what classical communication configuration we allow between the 3 parties. So for instance, if we allow two-way communication between both Alice and Bob and Alice and Eve, then we obtain this first quantity here, which is just the maximum of the two-way distillable entanglement of rho AE and rho AB. And similarly, depending on the other 3 communication configuration, you can define the other 3 relevant max distillation rates. And similarly, we can define fully undistillable, the notion of full undistillability, which basically just means that we say that this tripartite pure state is two-way fully undistillable if the first quantity here is 0. And two-way basically means that you allow two-way communication between both Alice and Bob and Alice and Eve. And similarly, you can define 1, 2, 2, 1, and just simple one-way full undistillability by making the other 3 quantities 0. All right, so this is like the basic setting. And now let me briefly describe what our main result says. So basically what we kind of resolve a tripartite variant of the NPT bound entanglement problem. More precisely, we have a tripartite pure state psi that is shared between Alice, Bob, and Eve. And what we claim is that the following statements are equivalent. So the first statement says that both rho AB and rho AE, the 2 reductions, are separable. This is equivalent to the 2 reductions being PPT, which is further equivalent to the tripartite state being two-way fully undistillable. So in this tripartite setting, two-way full undistillability is indeed equivalent to the PPT property of the 2 reductions. And it is in this sense that the NPT bound entanglement, the tripartite version of this problem is solved. And this is not and even further, we can actually say something more. These 3 statements are further equivalent to the state being 2, 1 way fully undistillable, and also 1, 2 way fully undistillable. Now, clearly, if the state is 2 way fully undistillable, meaning 3 holes, then 3 implies 4 as well, because you're just cutting off a backwards communication line from Bob to Alice, right? But 4 implies the implication, the reverse implication is not is the non-trivial one, because it is certainly reasonable to imagine that this quantity is 0, but allowing backwards communication from Bob to Alice, makes the quantity on the third statement non-zero. So the reverse implication is the non-trivial one. And just so that we are on the same page, let me describe the same thing again now with this figure in mind. So let me recall that we have 3 parties. They share a tripartite pure state psi, and the task is for Alice to distill entanglement either with Bob or with Eve, depending on which state gives her the best rate. And our result basically says that if any one of these 3 communication configurations is useless for the stated task, then so are the other 2. And this happens precisely when the tripartite pure state is such that both the reductions rho AB and rho AE are separable, which is further equivalent to the reductions being PPT. All right, so let me quickly state a very simple corollary of this result, which can be considered a partial resolution of the usual NPT bound entanglement problem of the bipartite case. So basically, the corollary says that if you have a bipartite state which is not PPT, then either you can distill entanglement from the state itself, or you can do it from its complement, and this is in the two-way setting. And why is this true? Well, I mean, if you assume on the contrary that you cannot distill entanglement from both rho AE and rho AE via two-way LOCC, then from the previous, our main result, we just saw that this was equivalent to both the reductions being PPT at the same time, which just immediately leads to a contradiction because we assume that rho AB was NPT to begin with. So this shows that if you have an NPT state, then even if you cannot distill entanglement from the state itself, you can do it from its complement. And so this kind of resolves a kind of like a partial resolution of the original bipartite formulation of the NPT bound entanglement problem. All right, so let me now quickly go to some ideas for how this result can be proved. So basically what we exploit some entanglement or distillability properties of low rank quantum states. Before stating what exactly I mean by low rank state, let me recall the hashing bound, which basically says that for any bipartite state rho AB, the coherent information of the state is an achievable rate for one-way distillable entanglement. And the coherent information here is just the entropy of the reduced state on B minus the entropy of the actual state itself. So if your rho AB is such that its reduction on the B subsystem is maximally mixed, then this hashing bound immediately tells us that the one-way distillable entanglement is going to be at least as large as log times RB, because the entropy of the reduced state now is just the maximum possible. And the entropy of the original state is upper bounded by the log of the rank of the state. So you immediately obtain this bound, and so you obtain a bound on the two-way distillable entanglement. And if you assume that the rank of your state is strictly smaller than the reduced rank, and this is the low rank assumption, then this quantity becomes non-zero. And so every low rank state which satisfies this condition is two-way distillable. But we want to get rid of this condition here because we don't want to assume initially that your reduction on B system is maximally mixed. So what we have is we have this theorem. So for any quantum state or for any bipartite state rho AB, which is of low rank, meaning that the rank of the state is strictly less than the rank of the reduction on the B subsystem, we have this bound on the two-way distillable entanglement. Instead of having this rate, we now have this rate multiplied by some factor. But the point to note here is that this is still strictly bigger than 0. And so every low rank bipartite state is actually two-way distillable, and we actually have a lower bound on this quantity. And the way to prove it is that we basically apply a local filtering procedure. So Bob selects this kind of a generalized measurement corresponding to 2 outcomes, and one of the outcomes correspond to this measurement operator, and which is basically defined as follows. You take the reduction on B and you take the inverse of the square root of that. And this is understood to be taken on the support because this operator may not always be invertible. And so after Bob applies this filtering procedure, you get this filtered state rho prime, which is just given by this expression. And why are we doing this? Because now for the filter state, the reduction on B subsystem becomes maximally mixed. So you can now apply the hashing bound, and which gives you the rate. But now we want to take into account this probability with which this operation succeeds, and this gives us the factor in front of this rate. A crucial point to note here is that two-way communication is essential in this proof, because after applying this filtering operation, Bob would want to communicate back to Alice to say that the operation succeeded. Because if it did not succeed, then they would have to kind of discard the states for which this operation failed. And so two-way communication is essential here. And this is why the proof fails if you just allow one-way communication from Alice to Bob. In fact, what you can show that even though all low-rank states are two-way distillable, which we just proved, they may not always be one-way distillable. And you can construct concrete examples of low-rank states which are two-way distillable, but not one-way distillable. However, if on top of the low-rank assumption, you assume something more, which is an additional rank constraint given as follows. So what you do is you assume, first of all, the low-rank assumption, the low-rank constraint, you assume the low-rank constraint, and then you assume that there exists a pure state on Alice's subsystem such that the rank of this object is this. Now, let me clarify what do I mean by this object. So this rho phi sub B is basically like a partial trace over A, but with respect to this pure state on Alice's subsystem that we have assumed to exist. So you can show it very easily that this object has always rank, which is upper bounded by the minimum of the rank of the original state and the rank of the reduced state on the B subsystem. So this bound always holds for any pure state on Alice's subsystem. But what we are assuming additionally in this theorem is that this bound actually gets saturated for some pure state phi A. So just to summarize, if you have a low rank quantum state which additionally satisfies this rank constraint, then you can actually distill entanglement by just using one-way LOCC. And the proof here is quite similar. Instead of now Bob applying the filtering operation, it is Alice who applies the filtering operation, which is defined in exactly the same way as before. But now, since it is Alice who is performing the filtering, she can communicate the results of the operation to Bob, because Alice to Bob communication is still allowed, and they can discard the states for which the filtering failed and proceed with the protocol, with the rest of the protocol. But now the crucial point here is that now, instead of the reduction on B being maximally mixed, it would be the reduction on A that is maximally mixed. And which basically means that this filtered state rho prime can now be considered as a valid choice state of some quantum channel phi from A to B. And now our idea is basically to show that this channel has positive capacity to transmit information, and then relate the distillable entanglement of the choice state to the capacity of the channel to send information to obtain the desired result. In other words, we want to show that this channel has strictly positive coherent information. And this combined with this bound, which basically says that the distillable entanglement of the choice state of any channel is at least as large as some dimensional dependent factor multiplied by the coherent information of the channel. And this holds for any channel phi. So if we assume these two things, then it's clear that since the LHS is positive, the RHS is also positive, which is exactly what we want to show. We want to prove positivity of the distillable entanglement of the state that we started with. So we want to prove these two things. So let me first tackle the bound. I mean, I'm not really going to tackle it. This requires a certain teleportation argument. And for those of you who are interested, you can look up the paper. So I'm just going to assume that this bound holds. And now, in order to show positivity of the coherent information, let me first actually recall, for the benefit of the listeners, what exactly is this quantity. So this coherent information for any channel is defined as follows. So you basically, Alice takes a pure input state, a bipartite input where A prime is some reference system, and the A subsystem is sent through the channel phi, and then you compute the coherent information of the resulting state, and then you optimize over all possible inputs. And this gives you the coherent information of the channel, and the regularization of this quantity gives you the full quantum capacity of the channel. And we want to prove that this quantity is positive, and we we do this by applying some recently obtained results. So basically, results by Vikesh Sidhu and by me and Nilanjana from last year, they can be used to show that if phi from A to B is a channel such that its Choi state, the rank of the Choi state is strictly smaller than the rank of the reduction of the Choi state on the B subsystem. If this is the case, and on top of it, if there exists a pure state input phi such that the rank of the channel acting on the state is this minimum of the two ranks, then your coherent information of the channel is positive. Now, these two conditions seem pretty familiar because these are exactly analogous to the conditions that we originally assumed for our state. And so these conditions that we assumed on our state translate to the assumptions that are required to show that this channel phi has positive coherent information. And so this is kind of the main technical result of our paper. This allows us to use the techniques that were recently developed to show positivity of quantum capacity of the channel to actually study distillability of quantum states via this bound, which is also like a slightly non-trivial result. All right. So now, if we have this theorem, what we can now establish is this result, which basically says that if you have a bipartite state rho AB such that its complementary state rho AE is one-way undistillable, then the following quantities, the following statements are equivalent. Basically, the separability of the original state becomes equivalent to the PPT property of the state, which is further equivalent to its two-way undistillability. And the way to prove it is, first of all, observe that 1 implies 2 and 2 implies 3. The forward implications are trivial to prove. So we just need to prove that 3 implies 1. And what we just proceed, we just straight away apply the previous result. So if we assume that the 3 is true, then since rho AE is one-way undistillable, it must be the case that rho AE satisfies this rank assumption, right? It cannot be low rank because then our previous result would show that it is actually one-way distillable. So since we assume that rho AE is one-way undistillable, we must have either that rho AE is not low rank, or it might be the case that rho AE is such that for all inputs in pure input states on Alice's side, the second rank constraint that we assume gets violated. So the previous theorem requires these two conditions together, and if we negate this, we get an OR negation. Either this is not true, or the second constraint is not true, which is precisely what we are showing here. And then the point is that once you have these two conditions, we can already exploit some previously known results on entanglement properties of low rank states to reduce our result. So if the latter condition is true, then you can use the result by Chen and Dokovic, I believe, from 2011 to actually prove that the rho AB is two-way distillable, which contradicts our assumption. If the former condition is true, then you can apply some previous results by Hrodecky and Vidal, Chirac, it's early results from 2000s, and relatively more recent result by Chen and Dokovic, I believe, again, to show that your state is separable. So the crucial part was this first reduction in which we employed our previous theorem, this one. And then you can use previously known results to obtain the desired statements. At this point, I think I should mention that a similar result was earlier obtained by Hayashi and Chen in 2011, which obtains the same equivalences that I just explained before, but they assume that the complementary state is PPT, which is like a much stronger constraint than just one-way undistillability. So PPT property in particular implies two-way undistillability, which further implies one-way undistillability. And from two-way going to one-way, this implication is strict. So this can, in other words, this result can be considered as a generalization in some sense of this earlier result that was obtained with a much stronger assumption on the complementary state. And then using very similar techniques, you can actually prove that if now, instead of just one-way undistillability of the complementary state, if you now assume two-way undistillability of the complementary state, then in fact, separability, PPT property, two-way undistillability, and one-way undistillability of the original state rho AB all become equivalent. And I'm not going to go into the proof of this, but the idea is very similar to what we just saw earlier. And now if we assume that we have these two theorems, then what the proof of our main theorem becomes almost trivial. So let me recall what our main theorem was. Our main results basically said that if you have a tripartite pure state psi ABE, then these 5 statements are equivalent. Now, note again that forward implications are again trivial to obtain. 1 implies 2, 2 implies 3, 3 also implies 4. And so let's just see how we can obtain the first statement from the fourth one. So if we assume 4, then what we are basically assuming is that the rho AB state is one-way undistillable. And we just saw that if this is the case, then two-way undistillability of the complement is equivalent to its separability, right? And similarly, 4 also says that rho AE is two-way undistillable. And if this is the case, we saw from our previous result that one-way undistillability is equivalent to separability. So we obtain our desired result. I guess that's about it. That's all what I had for this talk. These were some of the references that I used. Thank you for your attention, and I would be happy to answer any questions that you might have.
Thanks, Advik, for an interesting talk. So is there any question? You can also type your questions into the chat as well, or mute yourself to just speak up.
Okay, I have a question. Yesterday, Felix said that the by PPT conjecture is proved for quantum channel. So I'm wondering whether the theorem, I mean the first and the second one, can be used to prove
exactly.
By PPT conjecture.
Yeah. So all of the theorem in the language of quantum channel basically says that if the channel and its complement are both PPT, then they both must be entanglement breaking at the same time. Yes. So the first and second statements is actually the resolution of the bi-PPT problem that was raised by Felix and Christoph in their paper.
We know that it is not easy to prove that, but here it seems that the proof is,
yeah, I mean, the bi-PPT paper was actually also, I mean, I was one of the co-authors of that paper as well, and that was kind of the bi-PPT argument kind of motivated me to kind of generalize this result further. So the bi-PPT conjecture, the resolution of the bi-PPT conjecture is just equivalence of these first two statements here. But now this theorem is kind of extends that result even further to include the equivalences with two-way full undistillability and these other full undistillability statements.
Okay, thanks.
Thank you for the question.
Is there any other question?
Well, I mean, if there are no questions, let me just say that the actual NPT bound entanglement problem is still open. I think I forgot to add an open problem side. So, I mean, yeah, so this is like kind of like a partial resolution of the NPT bound entanglement problem, but it's only partial and the actual problem is still open. the problem is to tell whether every NPT state is two-way distillable or not.
Okay, thanks. So with that, let's thank Satwik again for a nice talk.
All right, thank you.
All right, so let's move on to the final talk of this session. So the next speaker is Marco. Can you share the screen?
Yes.
Okay, great. So let's go to the final talk of this session. The speaker is Marco Tomamicio, who is going to tell us about the chain rules for the quantum channels. So Marco, please.
Okay, thank you very much. Yeah, thanks to the organizer and everybody attending, and I guess all the people attending online or watching it later. So this talk is maybe not going to take the full time slot, and the reason for that is that it's actually quite simple. So the results we have are kind of a simplification of chain rules for quantum channels that were known before. There are some new ones as well, and the proofs are very simple. So I think that the main thing I want to sell you here is that the simplicity of the proofs, and I will actually be able to show the proofs. They're that simple. Okay, so let's get started. This is just repetition. I mean, I guess most of you here know Renyi divergences. They're defined as they are here, and we also know the limits, of which we mostly care about the infinity limit, or the maximum log likelihood ratio, and the Kullback-Leibler divergence. So this is just as a preparation, because I want to show you first the chain rules that we're interested in the classical case. So here we just have two distributions that are generated by a channel, like P and Q are the joint distribution of channel input and output. And then by data processing inequality, obviously we get this inequality, right? Because by a partial trace in quantum language, or just taking a marginal, we reduce the relative entropy, or it cannot increase. Good, and so then the latter expression on the right-hand side, we can rewrite it just using the definition of the quantity. And what we used here is obviously that that the input distribution kind of factorizes, right, just by definition of how they done. I mean, we could always do that for any joint distribution, just pull the marginal out and then have a conditional one on the other side. Now, the point here is that what we can now do is replace the second expression, so the sum over y, by just, that still depends on x, right? So it doesn't perfectly factorize, but we can replace it by taking a maximum over x, and then we have expressions that factorize. Okay, and if you do this, then the whole thing becomes additive under the logarithm, and we get an expression like this. So, and this is the kind of thing we want to investigate. So the question for this talk is kind of finding quantum versions of this inequality. Now, you see, the way to interpret this is that here we're looking at the divergence between channel outputs, and we want to compare this to the divergence of the channel inputs. So kind of in some sense, the distance between Py and Qy has two sources, One of them is the distance between the input distributions. That was already there. And the second part is somehow a measure of how far these two channels can bring, how far apart these channels can map different inputs. So we're taking a worst case here, maximize overall inputs, and then look at kind of how different the output distributions are. Okay, so we are to decompose the divergence of inputs with outputs in terms of inputs and the channels themselves. Now, the quantum generalization will look a little bit different. But before we can phrase that, I just need to introduce a little bit of Renyi entropy foundations. In a sense, so this is kind of a way of looking at it that Gilad Gur and I kind of advocate. So one way of defining quantum generalizations of Renyi divergence is by looking at a minimal and maximal divergence that satisfy data processing, and we can define them using by kind of mapping them to the classical question. So in one is well known. This is the measured relative entropy. So we just look at the classical Renyi divergence after we measured, and then take supreme overall measurements. And the other one, maybe a little bit less known, we take the infimum overall preparations of rho and sigma. So we look at classical distributions that can be used to prepare rho and sigma using the same preparation map. This has been first pioneered by Matsumoto, this kind of approach. And they are, it's easy to show that these are the maximal and minimal, or in the other order, the minimal and maximal generalization of Renyi divergence, in the sense that all generalizations that satisfy DPI are in between them. And they coincide only if rho and sigma commute. So, okay, now we will also need, we will actually need this variational construction, but it's just kind of good to know that at least in some parameter ranges, we actually have a closed form expression for this quantity. So this is the maximal one. And in this range, it's also additive and kind of has nice properties and converges to the Belafkin-Zastevsky divergence in the limit alpha to 1. Now, for the minimal extension, that one, as you said, is known as also the measured relative entropy or measured divergence. It's not additive, but we can bound it by taking a regularization. And so this regularized quantity now has a nice closed form, which is the sandwiched Renyi divergence. So this regularization, what it does is it makes the quantity, it forces the quantity to be weakly additive. In this case, it turns out that it actually makes it additive. So in a sense, this is the smallest Renyi divergence that is satisfies DPI and is also additive. Yeah, it has many applications, as we've seen in this conference. Good. So now I can formulate the one-shot chain rule first. So here, this is formulated in terms of this D alpha, which is a general Renyi divergence that we don't need to specify exactly what it is, apart from the fact that it has to satisfy this property. So if you have CQ states, then it has to factorize in this way. Well, not exactly factorized, but in the same way as we had the classical problem, we are able to pull out kind of the first marginal out of this Q alpha. And this is true for all the kind of quantities that we're usually interested in. So if you have this property and data processing, then we can show this inequality here. So, which we call now the one-shot generalization of these chain rules or channel chain rules. So here, the important thing is that, right, in the classical case, we just needed to take a supreme over X. Here we take a supreme over all input states, but there is no need, there's no regularization here, and there's also no kind of stabilizing system. So this is just a supreme over states of the input space of the two channels. And our inequality now relates the divergence of the outputs with divergence of the inputs plus this kind of channel divergence. So this in itself is kind of new. There's one special case that immediately follows is when you take the hat, everything as the hat quantity. Then this version has been known, and some other versions were not directly known, but some special case of this at least have been known. Now the undesirable thing about this is somewhat that we don't really like this very much here. So this one is usually too large. So later on we want to replace this. But first I'll show the proof of this inequality, or this is a sketch. And it's really simple. So what we do is we first use the definition of this d hat, right? And the definition was that we can find some states, classical states, P and Q, and a preparation map that maps them to rho and sigma, such that the equality here holds. So that gives us a decomposition also of rho and sigma in terms of now this preparation map instead applied to the basis states, right? The classical states that we started with. Okay, so we get these tau x quantities. Good. So how does the proof now work? Well, the first part is the same as classically. We just relate kind of the output states with the joint input output states. But here it's kind of this decomposition of tau is used, right? And it's the same decomposition on that works for both rho and sigma. You see, if you trace out the X system here, then because of the linearity of the map, right, this just gives you E applied to rho and F applied to sigma, respectively. And so we needed this kind of joint decomposition of the two states. So once we have this, then we can just do the classical argument. So we first pull out this pxqx and then bound the second part using a maximum. And then we can further relax it by taking the maximum, not just about this tau x type of states, but general states. And that's exactly the definition here, right? The divergence of P and Q gives us this d alpha hat, and then we get the channel divergence on the second term. Okay, so proof extremely simple, fits on one slide. previously there have been very complicated proofs of the same, or of special cases of this. Okay, yeah, in particular, this by Fang and Fazi, there was a proof for this for the hat quantity. That was somehow limited in scope, so only for alpha in 1 and 2, and also required a stabilization in this channel divergence, which we don't need, or kind of, well, they also had a stabilization in the first quantity. So in a sense, we can recover that from ours. Okay, good. So that's the first result. Now, as I said, we are not perfectly happy with this hat quantity. So we want to find a chain rule that, in terms of quantities that we are more used to, and this is done by regularization of this one-shot rule, essentially, where we now define this regularized version of the channel divergence. So here, for the channel divergence, it's really this regularization is non-trivial because this quantity is generally not additive, but certainly it's monotone in n. So we can replace a limit with the supremum here. And the point now is that we have this inequality where on the right-hand side we have this regularized channel divergence, and on the other two terms are in terms of the sandwiched Renyi divergence. There is a small issue, so this holds for all alpha larger than 1. In the literature, we also have this result for actually alpha equal 1, but we cannot recover this from our result. And the point that the reason for that is kind of a deeper reason, namely that for these regularized quantities, when we take the limit alpha to 1, then we don't actually know if they're continuous at alpha equals 1. So this problem occurs here. It occurs in many other problems, for example, this generalized Stein's lemma and so on. But this is one case where we just don't know how to take the limit at this point. But there is a separate result that shows that this also holds for alpha equals 1 by a group of Renato Renner and many co-authors. Now, yes, so one thing one can simplify to get another known chain rule is replacing this d alpha infinity with, in fact, the d infinity quantity, which is additive. So we're just kind of replacing d alpha with d infinity, and then we can drop the regularization. And that result was also known previously. Okay, so how do we get to this quantity? So here I'm giving a sketch for those who kind of are familiar with these types of arguments. They will be easily able to complete the argument, I think. So the idea is to do pinching. And so we apply the one-shot rule actually for these commuting states here. Right? They are commuting. So when we do this, we can obviously just apply the one-shot chain rule. But now the thing to note is that this d hat here, the second one, right? This is now evaluated for commuting states. So in particular, we can replace this d alpha hat with the d alpha tilde if we want, or any other quantum generalization of Renyi divergence. By definition, it's just they all have to collapse. Good, so that's one point. Then the second point is that this first expression, we can simplify using the pinching inequality. Essentially, it tells us that in this quantity here, we can remove the pinching, just losing a polynomial in n factor or additive contribution. And then obviously once we went back to row tensor n, then it becomes additive, and so we just pull out the n. Okay, so that is where the pinching inequality is used. Well, that's essentially because the alpha is already yeah, this term we don't need to do anything, right? It doesn't actually depend on the input states. So this will already have the right form once we divide by n and take the limit. So okay, so I didn't. Let me maybe use a different color. So for this quantity, as I said, we can replace it with the pinched. Sorry, with the sandwiched one, and then just use data processing, because the pinching is data processing, so we can upper bound it with n times the sandwiched. So that part is also very simple. And I mean, if you combine these things, then you have proven the statement. Good. So that was it. That was all I want to say. So I gave you actually the almost complete proofs of our results. It recovers many of the known chain rules for channels. We do discuss some applications for channel hypothesis testing. This has mostly to do with the fact that we don't need this stabilizing system. So that is interesting in some applications when we don't have quantum memory and want to show converse bounds. But mostly, I think the contribution here is to giving simple proofs for the existing results and generalizing them slightly. Yeah, so thanks for your attention.
Thanks a lot for the interesting and clear talk. So is there any question?
It was too clear.
So I just wonder, like, your technique, would it allow you to sort of extend this whole like chain rule thing to the higher level of like a super channel? Like, can you consider like the chain rule for super channel, for instance?
I haven't really thought about how that would look like. But it's an interesting question. Yeah, we haven't thought about extending in that direction. Yeah, I'm trying to think how one would even formulate it. So maybe we can discuss it at some point.
Yeah, that sounds interesting. So if you have any other questions, please feel free to type into the chat or unmute yourself to ask directly. Yeah, maybe it's too clear.
It's too simple. It's too simple.
Which is good, I guess. So yeah, if there's no other questions, and
okay, I have one question. So
okay.
I was interested in how can you apply your result to channel hypothesis testing?
So in general, if you have a kind of adaptive strategies, right, you need to bound the total entropy. So the way this is usually done is by using chain rules, or one way to do it is to use chain rules. Where you kind of, you know, so you start with I haven't actually worked on this topic. Maybe Mark would probably know better than me. This you start with right. You want this quantity in the end. This is going to be the strong converse rate, for example. But you need to decompose it. But yeah, sorry, I'm not able to answer your question very well at this
conclusion expected? What kind of conclusion? Maybe it's in the case of you are considering the future channel, and you can show that the strong converse exponent cannot be improved by adaptive method. This is your expected conclusion.
Yes. But our chain rule would maybe allow to. I mean, this is all known, right? This is not results from this paper. What our chain rule allows is maybe to deal with the case where you don't have quantum memory.
Don't have quantum memory.
Yes, but as far as I know, we haven't looked at this in detail.
Okay. Looks interesting.
Is there any other question? All right, if not, so let's thank Marco again for a nice talk.
Okay.
And I would also like to thank all the speakers in this session. And I will see you guys in the second session of today's conference. So I see you there.